is that. Okay. So today's lesson, lesson 58, we're actually going to finally prove the theorem that, well, one version of the existence and uniqueness theorem for first order equations. Okay? But before we start, we're going to talk about sequences of functions. And there are examples in the book of sequences of functions, but I'm going to give you my own examples so you guys have some different things you can look at. So, you guys definitely studied functions for the last 3-4 years. Sequences, where did you study that? Calc 2, you studied sequences. You study infinite sequences, right? And then you also studied something else that's related to sequences. You studied series, infinite series, right? And you learned that the sum of a series is actually the limit of a sequence, the limit of something called the sequence of partial sums. So I know you have that all in your background. But you're going to learn some new things here about sequences. Well, first of all, what do I mean by a sequence of functions? So here's my first example. I'm going to write Gn. Now, didn't you guys used to usually write a sub n for a sequence, right? I'm going to write g sub n of x. So this is, again, a whole bunch of functions of x that somehow are arranged in a sequence. And I'm going to make them be 1 over n times the sine of x. That's my first sequence of functions. So what do I mean by that? Well, I mean, for example, g1 of x is sine of x. And then I'll do g2 of x is, well, I guess it would be 1/2 the sine of x, right? So what I'd like to do here is I'd like to graph some of this. Okay. So I'm going to use a coordinate system over here. The nice thing about these functions is that we're very familiar with them, right? So sine of x I know is a wave that goes through 0, 0. And I guess it goes as high as 1 and as low as -1, and it's periodic, right? So there's that. And then if I were to graph g2 of x, what does it look like?
Same period, but
different amplitude.
Different amplitude, yeah. So it's going to have the same zeros, same period. I guess it's actually a little bigger than this. It goes down to half, right? And so it'll go down to -1/2. I'll go up to +1/2. And of course, if I did G3, it would be a little bit smaller of a wave, right? But you start to understand what's going on here. And so, here's the game we want to play with sequences of functions. Actually, you probably know the game. It's this. What would be the limit as n goes to infinity of Gn of x?
Zero.
So g of x here, I agree. G of x is 0. Why?
Because the amplitude is going to get infinitely small.
Yes. Yes. You guys follow that? So, I mean, this may be a first time you've ever thought of a sequence of functions converging to another function. Okay? But we just thought of that. And think about what we did last lesson. Picard's method of successive approximations, right? The idea today is going to be, look what this is, guys. This is a sequence of functions, right? Each function somehow gets closer and closer to the solution. All right? Well, that's what we mean. We want to converge to the solution. All right? Just Actually, in the same way that gn of x converges to g of x, which is 0 here. Okay? Now, there's an important mathematical definition I need to give you here. So, here's what I write. We say that gn of x, that sequence of functions, do you know what this arrow means? No? Okay. So that means converges to, okay, g of x. It's actually, so what I wrote so far is the same as what's up here, right? Gn of x converges to g of x uniformly. Okay? So I'm defining something called uniform convergence. Yeah, let me write that down. I need today something called uniform convergence if I'm going to do the proof for you. So that's my reason for kind of starting with just what are sequences of functions. So I guess to explain what uniform convergence is, the most helpful thing I could do is show you what uniform convergence isn't. I'm going to write another sequence of functions. We're going to think about what it converges to. And your book has more examples, but let's do this. Let's take f of x. Here, fn of x. This is going to be a sequence of functions defined by x to the n power. That's a pretty simple sequence, right? And let's restrict ourselves to the open interval 0, 1. That's what I want to think about. Okay? So what's going on with this sequence? Well, let's draw a picture. I guess I'll draw the picture here. So why did I pick 0, 1?
Because beyond that, it's really not going to get past there. I mean, because it's going to start, each one is going to start being exponential and faster and faster.
Well, they definitely have different growth rates, no doubt about that. What happens what happens at 0 and at 1 for these functions? I mean, let's list some of them here. So what is f1 of x? Well, it's just x, right? What's the graph of that look like?
It's 45 degrees.
Yeah, 45-degree angle line, yeah. And it goes through what points? Well, 0, 0, and also 1, 1. What about f2 of x? That would be a parabola. Where did the parabola and the line intersect?
Is it 1?
0, 0, and 1, 1, right? Isn't it true that every one of these functions is going to go through 0, 0 and 1, 1? Right? 1 to the nth power is 1, 0 to the nth power is 0. So there's a reason I did pick this, okay? Let's do another one. Let's do f3 of x, which is x cubed. I guess my question is, do you know what the graph looks like? Well, that's a cubic graph, I know that, but how about compared to these?
Is it going to come out a little bit further and then more of a sharp turn
Do you guys agree?
up?
Like, I like to just think about a half. What's a half squared? A fourth. But what's a half cubed? An eighth. That's only half as big, right? It's down here at that point. So I agree. I agree with what Joe said, that, x cubed is more like that. You guys with me? So, here's what I'm going to tell you. We say fn of x converges to a function f of x, which is what? Oh, what's this going to converge to? maybe we don't say this.
Wasn't it? You had another even power in
Yeah, like, you
there.
know, go ahead.
It's gonna get wider, isn't it?
It's going to get, like, if I do F4, it's going to be even lower, right?
I mean, it doesn't like turn into like an L looking thing, does it?
Well, that's interesting, right? What if I did the F1000? You know, we have Desmos. We can do this. Let me pause the tape and Let me pause the record. So I've graphed the first three functions on Desmos. Let's make a big one. So how about F100 of x? Because we want to kind of figure out what's going to happen as x goes to infinity. Equals what? X caret 100. I think this is what Jimmy was talking about. It's going to look more and more like an L the more you go, right? The 1000th power, right, would look more and more like this also. So we understand. The question is, what's the limit?
Some number right before it becomes completely vertical.
I mean, can I say this? Can I say that, kind of like in the first problem, can I say that f of x is converging to f of x equals 0 on the interval 0, 1? I mean, take a look for a minute. Here's the picture, right? If I just take a half, what's 1/2 to the 100th power? Well, it's 1 over 2 to the 100th. Really close to 0. Couldn't you say that's converging to 0, and this is converging to 0, and this is converging? Isn't it true that each point is converging to 0? Now, the only place you might wonder is, what about really close to 1? Right? Like, give me a point really close to 1. Point what? That's really close to 1. But if I give it a big enough exponent, give me a big exponent. How about that? What's that equal? Look what it said. It said that equals 0. Now that's not true, right? Why'd it put 0?
Approximately.
It's so close to 0 that it has so many zeros, well, you must mean 0, right? I mean, if I went up here and I got rid of a few, now it'll spit it out. But just add another 0 and it's like, ooh, and add another 0, it says forget it, must be 0. To me, that's really cool. That is true for any value of x. I don't care if it's 0.9999. The important thing to say here, it's true for any value of x on the open interval 0, 1. Now, this is not uniform convergence. What is it? It is what is called pointwise convergence. Now, I don't know if there's any math majors out there. Actually, I know from these 5, I don't think so. Aaron's not sure yet. But math majors will take a course called analysis, and one of the key concepts you study near the beginning is these two different kinds of convergence. We need uniform convergence. Why is this uniform? Basically because at every point, we're converging at the same rate. You know what I mean? I guess the point was, if you want to be within 1/10 of the limit function g equals 0, you just need to go to g10, and then you're fine. Like if you know what I mean? Like if I want Desmos to spit out 0, I could plug in n equals 100, it'll spit out 0 for the whole graph. For us, for the f's, it didn't spit out 0 when you're over here. But it would if you made this big enough. So yeah, we're converging to 0, but not as fast as you are other places. And that's maybe an idea for you guys of what uniform convergence is. Okay? So